hope you had a restful or productive extended weekend. We've got some derivatives to talk about, so what I want to do today is put together the remaining bits of some basics related to finding derivatives, finding rate of change functions, and then we'll be able to spend most of next week just practicing what happens when we stick all of these different sorts of details together in a single function. How can we take derivatives of more complex things? So in recitation, if you haven't already, you will later this week, get a whole bunch of rules to talk about and talk about how these kind of shortcut rules for finding derivatives. And we're going to go through some of those in here, prove some, kind of visually justify some. And then just do some more practice. We're not going to do a lot of practice of the basics, but we'll run across it in some slightly more complex problems. So if you have the basic function type derivative rules or rate of change function rules kind of in your head, it makes doing the rest of this easier. But we'll kind of go through a few more today. The ones we've talked about so far are this first one here, talking about functions that are power functions. X, the variable, raised to n, a numerical power. And it actually works for all numbers, although we haven't talked about proving why this works for things other than whole numbers. I'll show you an example today with a rational power, that it fits the same pattern. Constant functions, the rate of change is 0 because they aren't accumulating anything. They're maintaining a constant value. So the rate of change of their dependent value with respect to x or whatever the independent variable is 0 to something. Constant multiples of functions and sums of functions. So these are two specific types of functions versus these last two in the list right now, and we're going to add several to it, are examples of things you can do to already known functions. So for instance, if I had a power function and throw a constant multiple onto the front of it, make it a power function with a coefficient other than 1, then all I have to do to find the rate of change is multiply the rate of change of the power function by that same constant. We talked about this in terms of things you probably talked about with parabolas in early classes, and that coefficient makes it steeper or less steep. That steepness corresponds to rate of change of the vertical with respect to horizontal, or dependent with respect to independent variables. So it's just a multiple of what it would have been otherwise. And it's not just for power functions, it's for any sorts of functions. It's just that power functions are really the only interesting ones we've talked about thus far. If you have two added together functions whose derivatives you know how to take, whose rate of change you know how to find individually, then the sum of them, you can just add together the sums of those rates of change. And so for polynomials, multiple power terms added together, possibly with coefficients even, other than 1. You just do term by term. So just one term at a time, find the rate of change function of the derivative of each term, one at a time in a polynomial. Or for any sorts of functions who individually you know how to find their rates of change. If they're added or subtracted, subtraction can be just a -1 coefficient, you can just take the rates of change of the individual terms, the things separated by the pluses and minuses, and stick them back together afterward. So square root functions can be written as power functions, but I just want to show you that instead of just trusting me that we have to do that, this one's fairly easy to, relatively speaking, to show that the result of this comes out the same as using the power rule. And by the result of this, I mean by working from scratch, finding the rate of change over an interval of length h, and then letting h become essentially 0. We can see that the formula from that rate of change expression, that difference quotient, turns into an expected sort of expression involving powers of x that are 1 lower multiplied by a new coefficient. So our trusty rate of change formula with this particular f of x would look like so this is our f of x plus h, square root of x plus h minus the square root of x all over h, and then we let h approach 0, or we imagine h being essentially equal to 0 at the end after we've done some simplifying, because if we try to do that now, we get 0 over 0, which is not helpful in terms of imagining this. I get almost 0 on the top and almost 0 on the bottom. Not quite descriptive enough. So doing a little bit of algebra. And one thing you probably did in algebra, maybe even in pre-calc with expressions like this, well, if it was the other way around, lots of times I know you talk about rationalizing denominators, which is a way to standardize answer formats. We think of doing that same trick, but rationalize the numerator. Rationalizing denominators doesn't change the value of a fraction. It just changes the look of it, so it has a different looking denominator. Rationalizing the numerator, similarly, won't change the value of this, but it'll make it look different. And to rationalize when you've got a two-term expression, both with square roots, you multiply by the kind of like the inverse. You change the sign in the middle. So you get a difference of squares pattern, meaning if I multiply two binomial sort of things together, whether it's two actual binomials or two-term expressions, where the only difference between them is the sign between the two terms, we get this difference of squares. So a square of square root of x is a nice thing to have. A square of x plus h square root is also a nice thing to have. Those would no longer have square root signs anymore. Now, denominator becomes a mess, but let's take a look at what all happens with this. If we multiply the original rate function, this first set of parentheses was the original formation of this, that difference quotient f of x plus h minus f of x all over h for this particular root function, and multiply it by a messy form of 1, the denominator is going to become awful. I'll just leave it in factored form, but the numerator, using this difference of squares pattern, is going to be something that's easily simplifiable. I'd get the first term squared, leaving us just x plus h, assuming that we're dealing with real numbers here, so that when I square a square root of x, x is something, it's a real number. Squaring the square root of x, squaring the square root of x plus h, assuming those are both positive quantities underneath so that we have real expressions, I get this, where the numerator here is then just h. And so if the numerator is h and the denominator has a factor of h, you can factor those out, and I even separated this. You can see that it can be factored into, oh, well that, regardless of how large or small h is, that factor can be reduced, and we have an expression then just 1 over square root of x plus h times 1 over square root of x plus h plus square root of x, which, if we imagine h becoming essentially 0, so this part, if that's reduced out, that factor of 1, and I imagine h becoming 0, it's no longer an issue of, oh, it's almost 0 divided by almost 0. All I have is a sum in the bottom where I'm adding essentially 0 onto a x under a square root sign, which this square root of x plus h gets closer and closer to just being square root of x. And that's the only place that the h appears in the whole expression. The rest of it would simplify to this, which if you add something to itself, whether it's a x plus x or anything else, root x plus root x, that's 2 of them. Or I've got 1 over 2 root x to write it more succinctly. But if you notice, that is the same as what we'd get if we used power rule. If you step back and think about weird ways to write things with exponents, remember that square root of x is the same as x to the 1/2 power. And if I used power rule, the rule we talked about before, where it says x to the n has a rate of change function that's n times x to the n minus 1. So this power of 1/2 becomes a coefficient, and then I reduce the exponent by 1. 1 lower than 1/2 would be negative 1/2. And more fun with algebra rewriting, 1 over 2 times the square root of x is equivalent to 1 over 2 times x to the negative half. Remember that negative exponents are ways that you can indicate factors in a denominator rather than writing them in the denominator. So this is equivalent to that. And so using power rule or this rate of change formulation from scratch, we get the same result. You can think of it either way. You're always welcome to rewrite radicals with fractional exponents and use power rule. Square roots show up a lot in lots of common applications, so it might be handy just to, if you see a square root, know that it's derivative just off the top of your head. And so sometimes this is just listed as an extra rule. It's not really an extra rule, but it's a very commonly used variation on a theme or a very commonly used specific example of power rule. where it might be nice to just be able to write a fraction. And don't worry about, oh, now I have to rationalize the denominator. Not really concerned about rationalizing denominators. Usually we're looking for specific values of this rate of change function or its graph to look for patterns. And so the formulation of it isn't really the part that we're concerned about here. But if you did want to write this in a different form, it'd be, what, square root of x over 2x, if you multiply the root x over itself, if you want to do that. You're welcome to. All right, so let's take a look at, here, sorry. Let's take a look at some other functions. And instead of doing this x plus h stuff, let's just visualize them. Look at a graph of a function and think about what its rate of change function would look like, what aspects it would have. And we can actually graph from the x plus h format without knowing how it comes out in a nice closed form with h simplified out of the way or imagined to be 0. We can graph with very small h's using GC and kind of look and see if we're correct about our assumptions for what a derivative function would look like. And in some cases, we can, by looking at the visual, looking at the graph, you might recognize that graph, say, oh, I know what that's a graph of, and just know the derivative that way. That's not really a proof of it, but you can see where it would seem reasonable. You can see why the function that you have on your shortcut sheet seems reasonable and see that it actually comes from using our basic rate of change, our trusty x plus h difference quotient format. So there are ways to prove these others, but it's just a lot of algebra, and I don't want to spend all class doing algebra and specifically like trig identities and stuff for sines and cosines. So let's just take a look at, let's see, I think I have a GC window someplace. All right, so I put something very similar to this. I posted something called like a rate of change check on Canvas. It was just pre-made, but all it is what I've got is a place to, on this one, is a variation on that, to type in a function, to guess at a rate of change closed form function, what I just called R because it's easy to type. And I know that R sub f of x, which is the rate of change function just based on this difference quotient here. And I put h as a slider so we can look at the pattern as h gets smaller, but you can just pick a small number for a parameter value for h. So I'm going to hide the graphs of these for just a minute, hiding the graph of my difference quotient trusty rate formula. And, well, this one I'd have to type it in anyway. But let's say I was looking at what we just had, square root of x, which there's shortcut keys, but remember there's lots of commonly used sorts of hard to remember things in these menus. So if I want to think about the square root of x and its derivative function, well, I can graph this and say, okay, so this is what square root of x looks like as a function. It doesn't have any values to the left of 0 that are real numbers. We're only talking about real values here. In terms of accumulation, if I imagine this as an accumulation function, accumulation happens most rapidly near the endpoint and then slows down, and it doesn't have a horizontal asymptote, but it does get less and less steep as we go out. So thinking about the rate at which the y values are increasing with respect to the x, the farther I go to the right, the larger x gets, the smaller this rate of change should be. The smaller increments of y that we increase by. If I imagine like one block at a time, however large these blocks might be, every time I scoot over one block left to right, I'm going to go up less and less and less as I go farther right in the graph. Or for any size, as I move to the right, the corresponding change in y to change in x is getting less and less. So I'd expect that a rate of change function should have large initial values near 0, although right at an endpoint, if I think about what's the rate of change at an endpoint, there isn't going to be one. But right next to it should be large positive numbers indicating fast accumulation. And then afterwards, it should get closer and closer to 0 as I go on. So we know we got the function 1 over 2 square root of x, or we could write that in a variety of forms. But if I just look at what's the graph according to, since I defined this as f up here, this r sub f of x is already well defined. I just want to show a graph of it. Let's see, blue. There it is. So I'll zoom in a little bit. But you can see it's got positive values that start out large and get smaller and smaller. And if you were to zoom in closer, you'd see it doesn't actually have a value at 0. It's like a vertical asymptote for this function at 0. And then it approaches 0 as we go to the right. This rate of change, the blue, gets smaller and smaller and smaller. And in fact, it is a horizontal asymptote. But we also know what this function is because we just found it algebraically. And you can compare to see that you actually got the right function, or that that is valid, you know, at least visualizing wise. I've got, we said it was 1 over 2 times the square root of x. So if I graph this rate function, that red and blue are right on top of one another. The only way I can see that, I can see if I make my h larger and let it get closer and closer to 0, it hugs right onto where that red exact function that we came up with was. So this is an approximate blue function getting closer and closer to exact as we let h become closer and closer to 0. Those lie right on top of one another. So you can kind of verify that you've done your algebra correctly if that's what you're trying to do, using, you know, GC to assist. So let's take a look at different functions. I think I had on the screen y equals, I said a to the x or something. So let's suppose I have f of x equals 2 to the x. So I'm going to hide any rate functions for just a minute, so we can just look at y equals 2 to the x, which looks like this. I'm going to zoom out a little bit. So exponential growth function has a horizontal asymptote on the left side and grows more and more quickly as we go to the right. So this is y equals 2 to the x, or f of x equals 2 to the x. So its rate function, as you can see, well, the rate is small but positive over here, and then a rate that's moderately positive here, and then a rate that's higher and higher positive. Well, that's sort of the same trend in values as the function itself has. So, okay, near 0 but positive, and then always positive, getting more and more positive all the time. So let's take a look at, according to this f of x plus h trusty method here, I'll start with large values of h, what the rate of change of 2 to the x would look like. Looks pretty much like 2 to the x. It's a little bit different. As h gets larger and larger, I see it's not actually 2 to the x, but it's close, right? I'm going to zoom back in again. So I can see that, well, it seems to be an exponential type function. So the derivative of an exponential function seems to be, visually speaking, an exponential function. But it's not quite the same exponential function as we started with. So, for instance, 2 to the x is the black curve here. It goes through 1 on the y-axis, because anything to the 0 power is 1. Well, this, if it's supposed to be an exponential function, goes through something slightly lower. So if it were going to be an exponential function, it'd have to be multiplied by something slightly less than 1. Like, that looks, let's see, these are 0.25, so these little grid marks here, so maybe about 0.7, 0.8. Oh, wait, that's 0.75 there, so a little bit below 0.75. So if I were to guess, well, let's see, is this 2 to the x times 0.7? Well, that looks pretty close. This is with my h extremely small. It's not exact, but it's pretty close. So that's a weird number, though, just 0.7. Seems sort of random. So let's look at some other exponential functions. So what if I had 3 to the x and looked at its graph, which, again, it's the same shape of function. When I compare it to its derivative, it looks even closer. So 3 to the x and its derivative are extremely close together. Or if I zoom in to the vertical intercept, say, well, if this is an exponential function for 3 to the x's rate of change, 3 to the x's derivative, it's got to be something that's multiplied by something just a little bit more than 1. Looks like about 1.25 in this. So if I check, let's say, oh, I think this is 3 to the x times 1.25. Well, oh, that's when I had, let's see, that's too big. Sorry, this is 1.5 up here, so it's not 1.25. Maybe it's something smaller, 1.1. Oh, that looks pretty close. Those are right on top of one another. So the thing is that we have to figure out how is 2 related to something around 0.7 and 3 is related to something around 1.1. It's a weird number that we're not going to guess off the top of our head, but what this actually is, it's related to logarithms. It's related to the natural log of 3 and the natural log of 2, just as a separate line here. The natural log of 2 is 0.69. The natural log of 3 is just about 1.1, 1.09. In reality, these log functions, derivatives, are not times random decimals. The derivative of 3 to the x is 3 to the x times the natural log of 3. And ln is built in as a function to GC. It knows what that is. If I graph this versus the trusty function here, you'll see it does match up precisely. This isn't a proof using exponential, like fun with algebra and exponent rule stuff, but you can maybe see that, okay, that works. Let me try it again with the 2, or with a 4, something we haven't done. 4 to the x. Well, according to this, what seemed to be the case, 4 to the x times the natural log of 4. Yep, looking at these graphs, I only see 2 of them. The one that goes through 1 on the x-axis is the original black 4 to the x function. And up here we have the red is the succinct formula, the blue is the one with the h. As h gets smaller and smaller, it hugs right onto that 4 to the x times natural log of 4. So there's one special case that shows up usually again as its own derivative rule, even though it's not really different, it's just a nice special case. The number e, Euler's constant, is the base of the natural log function. E to the x looks just, e is approximately 2.718 something. It comes from a lot of different places. Algebra and trig are 2 different ways we can derive it. But e is built in as a constant to GC. It knows what e is when you type it. You can't assign a value to it. E to the x is just something between 2 to the x and 3 to the x. It's 2.718-ish to the x. And its derivative, well, it'd be, according to our pattern, e to the x times the natural log of e. But natural log is a logarithm base e, and the logarithm base e of e is equal to 1. Fun with logarithms. Review some log properties if you'd like. They can help you simplify in some cases. But e to the x times the natural log of e is exactly the same as e to the x just by itself. It's the times 1 is what's on there. So you can, the derivative of e to the x is itself. That sounds sort of weird. It's a rate of change of e to the x is exactly the same as the dependent variable values in e to the x, which is very strange sounding. But what that means about this, for instance, I know that e to the x goes through the point 0, 1. At this point, in that moment, the rate of change is also 1. If I were to go farther up the graph to where x equals 1/2, I don't really know the y value off the top of my head, but whatever the y value is, e to the 1/2 power, the rate of change, or the, visually the steepness of this is the same number as the y value in this graph. So the y values of, when these are superimposed on one another, they're exactly the same. The rate value and the dependent variable value of e to the x are the same. So in reality, that's what, if you ever took an Algebra 2 class and you talked about like compound interest and like think about, oh, like monthly compounding or daily compounding, and then there's that whole continuous compounding where you imagine like getting a little fraction of a cent every fraction of a second or something like that. In reality, the best way to describe continuously compounded interest is derivatives, and that's a little bit difficult for Algebra 2. But what that means is you've got this e to a power. It means if you have 4% continuously compounded interest, the derivative way to describe that is, or the rate of change way to describe that is, at any moment, the rate at which your money's growing is 4% of the current balance. So that 4% continuously compounded interest, that 4% is whatever the balance is, it's growing at a rate that's 4% of that current balance in dollars per year, or whatever the time frames are. So, in any case, derivatives of rates of change for exponential functions, quick rule, if I have a to the x, for any positive number a, I'm not going to have 0 to the x, and in fact, we're not even going to use 1 to the x, although that would be fine. 1 to the x is just the constant function 1. natural log of 1 is equal to 0. So it works out okay if a is 1, but usually just say a is a positive value. So we've got an exponential. It could be growth or decay depending on whether a is greater than or less than 1. But exponential growth with a base a, the derivative is said to be a to the x times some constant, but we decided that constant, not by proof, but just kind of visual justification, is the natural log of a, whatever that base of the exponent is. So if we're using e as the base, e as the value of a, then you don't have to write the times natural log of e. You can, and it's not wrong. It's just like writing a times 1, though, so it's not needed. So the rate of change of e to the x is e to the x. So stepping back a second from doing rates of change things and going back to accumulation, looking at this integral, g of x equals the integral from 4.5 to x of 10 to the t times natural log of 10 times dt. So we want to know what's the meaning of that and what else we can say. But if you notice the integrand here, 10 to the t times natural log of 10, that should look familiar based on thinking about, oh, if I'm integrating, if I'm finding accumulation, this is my m dx expression, or this is my rate of change of something. What is 10 to the t times natural log of 10, the rate of change function from? Yeah, just 10 to the t. So if I have something whose rate of change is this, the thing that's accumulating is accumulating with a closed form 10 to the t. Now we're only accumulating not forever, just from 4.5 through x. So if I wanted to talk about this expression here, this is the accumulation due to that rate that we see between 4.5 and x. But I know what sorts of accumulation happen. The sorts of accumulation that happen are in the form 10 to the t, where t takes on all the values from 4.5 through x. So I want to compare the beginning, 4.5, to the end, x, and figure out the net change. So it'd be 10 to the x, final, minus 10 to the 4.5, initial. And that's it. So we could talk about the meaning of this, or we could also compute an expression for a function. This is the accumulation between 4.5 and x due to this rate, be 10 to the x minus 10 to the 4.5, final minus initial, for something, anything that has this as its rate function. All right, so take a break from new expressions for a while. Take a look at this ugly thing. The pieces of this are all things that we've talked about in terms of how to find a rate of change function. So if this is function p of x, if I want to find r sub p of x, also known as p prime of x, or dp of x dx, there's a lot of terms. You can think about one at a time. There's some coefficients, some power functions, exponential functions, possibly some constants. See if you can write a closed form. Don't do the x plus h stuff, just using shortcut rules. And find the rate of change of this function p. So think of the structure of all the pieces. The parentheses at the beginning, it's tempting. If you want, you can multiply out and get rid of those parentheses, but you don't have to. You can think of that 4 as a constant multiple onto a function that's inside, like a sub-function here. 8 to the x plus x to the negative 8th. If I know how to find the derivative of that, I can just multiply it all by 4 to get the derivative of this slightly larger messy term. You can also distribute, but realize there won't be any 32s to the x. This is just 4 to the first. But whether or not you distribute this, it looks pretty similar. So if I said 4 times 8 to the x, the rate of change would be 4 times the derivative of 8 to the x, which with respect to x, the derivative of 8 to the x is 8 to the x times the natural log of 8, right? I'm going to put parentheses in there so that I can kind of see that that's a log expression, messy writing. And if you distributed, you'd also write time at plus 4 times the derivative of x to the negative 8, or you could just put parentheses around the derivatives of those first two terms. Either way. The derivative of x to the negative 8th. Well, that's a power function. It's not an exponential. Remember, power functions have powers that are numbers. Exponential functions, their exponent is the variable. They've got the variables in the opposite places from one another. So x to the negative 8, this is the subtract 1 from the exponent. If it's a variable up there, you know you're doing the wrong thing. So subtract 1 from this exponent, making it an x to the negative 9th power, and multiply on a coefficient that's what the old power was, negative 8. Now, I would say don't worry about simplifying. If you're going through something like this and write negative 32 in front, that's perfectly fine. Negative 32x to the negative 9th, or 4 times negative 8x to the negative 9th. Not really concerned about simplifying, just get all the calculus done. So that's this first chunk. Now, this is such a simple term, its rate of change is almost confusing, but rate of change, slope, steepness, change of y with respect to change in x. If my only function were f of x equals x, what's the rate of change for that function? 1, right? It's a line with a slope of 1. It's a constant rate of change. It's not 0. It's not a constant function. It's a constant rate of change of 1 for this term. You can actually apply power rule. Say this is 1x to the first. And so if you reduce the power by 1, you get x to the 0 power, which would be 1. But in reality, what's going on, this is just a constant function with a rate of change of 1. All right, then there's this term, minus 2e to the x. So I can think of that coefficient, negative 2, multiplied onto e to the x, whose derivative is e to the x. Best function ever. All right, then we've got another term, plus x to the 10.7 power. That's definitely a weird power, but that's definitely a power function. So its derivative is going to have x with one lower power, 9.7, and a coefficient that's what the old power was. And we've got two more terms here. This one we just dealt with in specific. Oh, square root of x, I don't even have to deal with that. I'll just put it, it's minus root x, so minus 1 over 2 root x, just remembering that shortcut derivative rule. And what about this last one? Is it an exponential function? Is it a power function? What? It's a constant, right? There's no x's in it. There's no variables in it. X's are a variable. E is 2.718. Squared means I'm like doing something. This is slightly less than 9. It's 8 point something, I'm guessing. But this is just a number. It's not changing as x varies. So its value is 0. You could write plus 0 if you wanted to remind yourself that you didn't forget about it, but that's rate of change is 0. But you don't have to write plus 0, just like you don't have to write times 1. And there are a variety of ways in which you could simplify and have it look slightly different from this, but anything algebraically equivalent is fine. Questions on this? Yes.
Is this what our master exam is going to look like?
Some questions like that, but we have a few more rules to talk about. So there'll be some, on the mastery test, there are 35 questions. 25 are pieces that look essentially like one term of this, just like find the derivative of negative 2 e to the x, find the derivative of x to the negative 8th, find the derivative of e squared. There are 25 questions that are just single, short, like, do you know your derivative rules? And then there are 10 questions that have more combined things. Some are like this, sums and differences. There are also some other ways that functions can be combined. Products, quotients, and compositions of functions, which you probably dealt with how to write all of those by combining like a function f of x and g of x kind of all at the same time in an algebra class at some point. We've got a little bit of work to do to figure out how to find the derivatives of those if they don't simplify nicely. How do you find the derivatives if they're combined in these strange ways? And that's where we're going to spend most of our time on second half of class today and all of next week working on how to deal with that. Because there's just so many different ways you can combine them that look different but that follow the same rules. I do want to talk about another few different types of functions though yet. So we'll get to that. Let me clear off this, however. All right, so what we've got so far, we've got power functions and constant functions and exponential functions. And I use the other notation this time. Instead of the r sub f, I use the prime notation. Don't let the notation throw you off. If you see prime notation, the r with the subscript notation, or even the ddx notation, those are all equivalent to one another. They're all finding rate of change functions. Or imagine that you're starting from something measuring accumulation. How does that accumulation change as the independent variable varies? So we've got some things covered, but there are many other types of things. So besides constant and power functions and exponential functions, which we've talked about, your mastery exam and the shortcut sheet you might have already received in recitation and talked about it. It's already also posted on Canvas. Includes logarithmic functions and their derivatives, which are the inverses of exponential functions, trig functions, and inverse trig functions, also called like arc trig functions. So I want to talk a little bit about a couple basic trig functions today, sine and cosine. We'll take a look at using GC again, take a look at the graph of, let's start with sine of x, and see if we can imagine what its rate of change should look like, and then find its rate of change function visually and take a guess at what it is, like we did with exponential functions. So let me see if I can change gears here. All right, so back to GC. Let me get rid of this, because this is not what I want. Done with exponentials for right now. And I'm going to hide this rate function for a minute so we can think about it ourselves first. But let's say I have a function sine of x. I'm going to have to slide this around. But sine of x, periodic function, looks like this. Periodic with a period of pi. Well, pi gets us halfway through. It repeats, but inverted, every other pi. So we've got 2 pi till the whole sequence repeats. But we've just got a sequence of values, then a negative of the same sets of values, and positives and negatives and so on. So it's a very symmetric sort of thing. Thinking about as if this is an accumulation function measuring something, I see that amount of something increases and then decreases and then keeps decreasing for a while and then starts increasing again. So the steepest spots on this, meaning the fastest rates of accumulation, are, well, right around the x-intercepts, every other one. The others are the fastest deaccumulation, the fastest decreases. So say, oh, well, I've got accumulation at its greatest point here and then its least point there, meaning highest positive number, most negative number. And I've got positive rates of change from 0 to, well, be pi over 2. And then from pi over 2 to pi, and then another half pi, 3 pi over 2, I'd have negative rates of change. and it repeats itself over and over again. So you can imagine the rate of change function for sine has to be something periodic, just like sine function is. It has to kind of go through its cycles over and over again through all the same sorts of values. But its highest points would be, well, like at 0, at 2 pi, at 4 pi, and so on. And its lowest points would be at the other multiples of pi, at 1 pi, 3 pi, and so forth. Oops, 1 pi, 3 pi's over here. So if we look at a trusty rate of change function here, and let's just calculator drool here, I'll make smallish h's. You see, okay, so that's periodic. This has this blue is the rate function. It's got its highest rate around 0, where this graph is the steepest or increasing the fastest. And then this rate function has its most negative at pi, when the accumulation function, the black line, is most steeply going downward. So question is this: what function does this look like? That looks like cosine. Now, cosine has a period of 2 pi, has maximum and minimum of 1 and -1. This seems to be the same function. Let's compare it. Let me put in, actually, I think r of x. I think this rate of change function is cosine of x. Well, I have h essentially 0 right now. You can see if h is, when I make blue more of an approximation than less exact, it's kind of similar. And the closer h gets to 0, the closer it gets to being right on top of the other. Those blue lines are just numerical computation errors, calculator errors. There's not actually any vertical lines that show up. It's just too close to 0 for the calculator to deal with it well sometimes. So the derivative of, or the rate of change of, sine of x is cosine of x. Well, that's kind of nice. Now we could actually do some trig substitutions with identities like sine of x plus h, using that sine a cosine b, that sort of formula. But rather than getting into remembering all your pre-calculus rules, just say, okay, that seems reasonable. So instead, let's not prove this today. The proof is actually in your textbook. Say, all right, the derivative of sine of x seems to be cosine of x. That seems reasonable, both in the fact that it's periodic and it looks to match up to the right values. So what if I were looking for the derivative of cosine of x? Well, let's see. Cosine of x, I'll put this in the first spot and unhide the graph. Cosine of x is the black graph, and this is its rate of change, the blue graph. Well, okay, makes sense again that it's periodic, because cosine, just like sine, goes through the same sets of values over and over and over again. And this blue graph looks, well, yeah, it looks like a sine graph, but it goes down first instead of up first, meaning between 0 and pi, this has negative values, and then it has positive values afterward. Sine of x is this way, the red curve. Negative sine of x matches up precisely with this, where this is my rate of change as an estimate, getting closer and closer to reality. So this, my exact function here, which again has that calculator drool error thing, the exact rate of change function for cosine of x is actually negative sine of x. Again, could be proved with the sum and difference identities for trig and some other facts about cosine of 0 over 0 sorts of things. But the derivative of a sine function is a cosine function. The derivative of a cosine function is -1 times the sine function. Why say a sine function? One of the main things that we're going to need to work on next week for a while is what's called chain rule. It has to do with compositions of functions, because it's like e to the x is e to the x, that's great. But I mentioned that compound interest, e to the like 0.04x, something like that. Oh, but there's other stuff in with those x's. So if it isn't just sine of x, if it's sine of some whole formula with x in it, we're going to have to account for all that other stuff. But the derivative of a sine function is going to involve a cosine function and possibly some other things if it's not just sine of x. Same with e to the x and 2 to the x and everything else, even square root of x. If it isn't just square root of x, if it's a square root of a whole other formula, a whole other function rule underneath, well, it's going to involve 1 over 2 times the square root of something, but with some other details to work out, which involves compensating for or accounting for all of the details in a function, but still using the basic structure that we started with. So chain rule is what it's called. It has to do with compositions of functions. It's one of the messier pieces. We'll save that for next week, but I'll have you read up on it between now and then. What I want us to take a look at for right now, though, is what to do if I have products of things or quotients of things who separately I know how to deal with. So, done with graphs for just a minute, but we'll talk about tangent of x, for instance, is a quotient of sine and cosine. Sine of x divided by cosine of x is tangent of x. I'm not going to try to do this visually because, well, here I'll show you. If I look at tangent of x, I'm like, well, I don't really know what this blue thing is, but it looks crazy. It's periodic, but not a sine or cosine curve, so not really sure how to guess at what that is. But since tangent is based on a combination of sine and cosine just divided, there's a way that we can get a formula for its derivative, tangent's rate of change, using sine and cosine, but unfortunately it's not just sine's derivative divided by cosine's derivative. Otherwise it'd be cosine over negative sine, which would look just like a tangent function, but inverted, look like cotangent kind of. But let's see, where were we? Here. So there's some inverse trig functions also, but constant multiples and sums and differences are easy. If you throw a coefficient on something, a constant multiple, to find the rate of change with or without that involves just, oh, well, multiply it on or don't to the derivative. Sum or difference of functions, that was easy. You just add or subtract all the different terms, rates of change together. But if you have a product of functions or a quotient of functions, it's not quite as simple, nor if you have a composition of functions, which we were just talking about. These three are the kind of more challenging rules of combining things, although products and quotients, multiplication and division, are essentially the same operation. They're very closely related. So the rules for how to deal with products and quotients are going to be very similar to one another. Composition, it depends on what you're composing, but we will get to all of this. So a product of functions. Let's prove this. If I have f of x times g of x, or if it's written fancy form, f times g of x, and I want to find its rate of change function using our x plus h difference quotient method. Well, if this is the general format for it, regardless of what precisely functions f and g are, I can say, all right, this derivative, and I just use the prime notation here, I'd take the function rule with x plus h as the input, minus the function rule with just plain x as the input, all over h, and then imagine h becoming essentially 0. So this looks like, well, how do I simplify that if I don't know what f and g are as functions? With trickery. And this is a trick that's used in a lot of math proofs. We're going to take this fraction, and in the numerator we're going to add in a term and then subtract it back out, which sounds like a dumb thing to do, but if you choose correctly, we can separate this into two fractions because, well, of the way that factoring works. So what I'm going to add in here is the stuff in red, add and subtract. I wrote the subtract part first. So I have f of x times g of x, or f of x plus h times g of x plus h, minus, now this looks like a mystery. How on earth do you come up with this? Plotting and planning. So I know where I want this to end. So this is just the proof of how this rule works. You're not going to have to repeat this all the time, but this is just, I'm going to have a succinct rule by the time we're done. I want you to see where it comes from. So if I subtract off f of x times g of x plus h and then add it back on, those red terms are opposites of one another. So I haven't actually changed the value of this fraction. I've just changed what it looks like. It's like making common denominators or rationalizing, doing fancy fraction stuff. But the nice thing about this is, if you look at the first two terms here, the way they're written, I've got a positive term and a negative term, and they've got one piece in common between the two of them. That's g of x plus h. If I look at the second two terms in the numerator, they also have one piece in common between them. They're both products. They both have an f of x in them. And So, all right, so I have some like terms. I can think about this, group this, and factor each half of that numerator, which again seems like a sort of strange thing to do, but in the first two terms, this g of x plus h appears in both of them. If I factor that out, I have f of x plus h minus f of x. That sounds kind of familiar. In the second half of the numerator, the factor that those two have in common is f of x. If I factor out f of x, what remains from those two terms is a g of x plus h and a minus g of x. So if you can see the pieces inside the parentheses, like the leftover part from factoring out common factors in both halves of the numerator, looks like our numerators from individual derivative expressions. Now, I'm going to split this into two fractions over the same denominator, h, because we're allowed to do that. And in fact, since I have a product in the numerators, let me just write one of them off to the side. You can see g of x plus h times f of x plus h minus f of x all over h would be the same as if I have this off to the side and over 1. Same with the second half. So I've got a g of x plus h times this expression, which ought to look familiar, plus f of x times this expression with g's, which also should seem familiar. So thinking about this, if I imagine now, well, what if I let h become essentially 0? Well, if h is essentially 0, then that last part I was just pointing out with the g's in the fraction, then this is the rate of change of function g. F of x times the rate of change of function g. If I let h become essentially 0, focusing on the first part, then this big fraction becomes the rate of change of function f, and well, this would become just g of x. G of x plus h, as h gets to be very close to 0, is essentially the same as g of x. So this whole expression, using prime notation, if I imagine h becoming essentially 0, as said at the top, this all simplifies to g of x times the rate of change of f plus f of x times the rate of change of function g. Now, it's not particularly short. It's not quite as easy as just how do I find the rate of change of two things multiplied together, just find their derivatives and multiply them back together. Unfortunately, that doesn't work. But in order to find the derivative of a product, I do need the derivatives of both factors of the product, but they get pieced together like this, in this format, where I have two terms, each of which has one of the original factors and the other factor's derivative. So mix and match, one each way. And since it's all multiplication and addition, it doesn't matter what order you think of these being done as, but it's just not f of x times its own derivative, but one factor times the other's derivative, the other original times the first derivative. So this is where that rule comes from. It looks kind of messy, but however you want to write it, you can write it with prime notation, with this d dx notation, with the r sub fg notation. But to use this, something like this. Now, I picked this problem because if you wanted to, you could clearly distribute and multiply this out to just have a polynomial sort of function. So we can compare what we get against using product rule versus what you'd get if you distribute. But take a minute. Again, product rule would be useful because I have this written as a product. You don't have to use product rule. You could distribute. But think about the derivative of, you can call this f and this g. Well, the whole thing's called f, so maybe pick some different letters, m and n. But I need the derivative of one times the original of the other, plus other way around. And each of these factors individually, if you don't distribute it, is really easy to find. Because each only has one part of interest. And again, if you're working on putting this together, once you finish doing the derivatives and putting the structure together, you don't need to distribute or combine like terms or anything like that. Don't worry about simplifying, in other words. But if you want to call these something like G and H, whatever, pick some letters to kind of remember that format. I want G's derivative times H and H's derivative times G. And it doesn't matter what order we do those two pieces added in, nor does it matter within each product which order I write the multiplication in. Commutative property. If I want to write this out, g of x, this first factor, whatever you want to call it, is, well, I've got one term with an x and one constant term. So its derivative would just come from this 2x to the fourth. What's the derivative of 2x to the fourth? Yeah, 8x cubed, or 2 times 4x cubed, right? And I take that derivative of g of x times the original h of x, or whatever you want to call these two pieces, plus other way around. I need the derivative of h of x, or the second part, the second factor, which again has a constant piece. That 7 doesn't contribute to the derivative in terms of when I'm finding h, this factor's own derivative. It'd just be the derivative of this part is 6x to the first power. So I'd do 6x times this first factor. Or written all out, I just put it in the order that I happen to type it here, but it doesn't really matter, like I said, the order of the pieces here, as long as I have these two multiplied and those two multiplied. It doesn't matter in which order the multiplications are written, nor in which order the addition is written. So 2x to the fourth minus 3 times 6x plus 3x squared plus 7 times 8x cubed. Although if you want to, obviously, we could distribute, and I know that this would start with, let's see, if I'd multiplied this out instead of using product rule, I'd get 6x to the sixth as the leading term of this polynomial. 6x to the sixth would have a derivative of 36x to the fifth. If I look down at this formation, I can find that 36x to the fifth. It's in two places. 6x times 2x to the fourth. There's 12x to the fifth. And over here I've got 8x cubed and 3x squared. That'd make 24x to the fifth. If you were to distribute out and simplify our product rule result here, you would still get something whose highest term is 36x to the fifth. And you can do the same with the other terms, but I don't really want to spend class time on distributing algebra stuff. But if you want to verify this for yourself, multiply this out using distributive property and find the derivative from its polynomial form. You'll see that it's exactly equivalent to, well, if you use product rule and then were to distribute out twice here. The nice thing about using product rule as opposed to multiplying out and using polynomials is, notice we didn't have to worry about, wait, if I multiply x squared and x to the third, is that x to the fifth or x to the sixth? And accidentally make a silly algebra error. All you have to do is subtract one from the exponents and place them next to one another. Answers in this form are perfectly fine and highly acceptable, and I like them better on your master exam. It's really easy to see if you know what your pieces are, and also you won't accidentally make a mistake with algebra if you don't do any algebra. So let's take a look at a quotient really quickly. If you want to find the derivative of a quotient, keep in mind that a quotient can be rewritten as a product, and in general that's not what we want to do. Like, if I have a whole big complex rational expression, I really don't want to write it with negative exponents and something around parentheses. That makes a really ugly expression. But for the proof of how we can come up with a derivative formula, a derivative format for dealing with functions that are written as division, I want to take this and make it look like a product, and then we'll be able to use our product rule. So There's a little bit of algebra involved. But if I think of this as f of x times g of x to the negative 1, or f of x times 1 over g of x. Now, this does involve some stuff that we haven't gone through all the details of, but I could think about using product rule, which says take f of x times the derivative of g of x to the negative 1. That's the only part that we haven't really had experience in doing, plus g of x to the negative 1 times the derivative of f of x. That's just our product rule. If we rewrite this quotient as a product, then here is an expression for how I can find the derivative. Now, in reality, we haven't really talked about how to find the derivative of a whole formula to the negative first power, but x to the negative first power, we know how to deal with that. We make it x to the negative 2 power and multiply by negative 1. It's actually similar here. But this is something called chain rule where this comes from. I just wanted to show you this, like, let's skip over the details of, wait, what is this? Where does this come from? But it actually does come from another derivative rule we'll talk about. I just wanted to save that for next week because it's a long one. But f of x times g to the negative first power is derivative, which does involve this negative 1 and a negative 2 exponent, just a little extra stuff. Plus g of x to the negative 1 times f's derivative. Or, and we could have done this with just really ugly algebra and f of x plus h sorts of things. But with a bit of algebra, and just trust me on this one, we'll talk about why this works next time, this g of x to the negative 1. It's called chain rule. Our derivative works out to be this expression for a quotient of function f and function g, with g as the denominator. So unlike multiplication doesn't matter what order you write it in, it's the same thing. Division, it does matter which is the divisor and which is the dividend, which is the numerator and denominator in a fraction. Also, subtraction, which you see appears here, does matter the order in which you do it. It has to do with, again, which was in the numerator and which was in the denominator. So in this result here, the derivative of a fraction type function, or any quotient, even if it's written with a weird division sign, the numerator divided by the denominator. The derivatives of the numerator and denominator are involved. And notice that the numerator here looks just like product rule, except with a minus. So the order is important. The part before the subtraction, the first part of the numerator, involves the derivative of the original numerator. The second part, or after the subtraction, the second part of the numerator involves the derivative of the denominator. So you've got this one derivative and one original product still. They're subtracted. Before the subtraction comes the numerator's derivative. After the subtraction comes the denominator's derivative. And then it is actually still a fraction by the time we're done, where the denominator of the overall fraction is the original denominator squared. Kind of skipping over some details of algebra and simplification, but just what I wanted to point out was that the rule for finding the derivative of a quotient is fairly similar to the rule for finding the derivative of a product. The difference between them, one, plus versus a minus, which that seems maybe reasonable for division versus multiplication, positive versus negative exponents in reality, and that the result is actually still a fraction, which maybe should make sense if you think of a fraction like 1 over x. The original was undefined at 0, so its rate of change function should still be undefined at 0. So if it's not exactly the same denominator, but it still has a denominator that involves the original denominator. So we aren't adding things to its domain by taking its derivative, which is good. We'd like the domain to still have the same exclusions as the original, because we shouldn't have a rate of change if we don't even have a function value. So here's another way to write this. Sometimes you'll see brackets. And again, it doesn't matter if I write f prime times g or g times f prime. That part doesn't matter. But the f prime part, or the numerator's derivative, needs to be before the subtraction. The denominator's derivative needs to be after the subtraction. And if you can kind of remember that product rule formation and what the denominator is, although this is a long-looking formula, you can get used to it pretty quickly. So let's take a look at tangent. So if you see on a shortcut sheet, it'll say the derivative of tangent of x is secant squared of x. So that looks unpleasant. But tangent is just sine and cosine in a quotient. So tangent of x is sine of x divided by cosine of x, whose derivatives we talked about separately earlier. So let me pull up my writing doohickey and play around with this for a little bit because I know it's going to... All right, so if I have, let's see, I'll call it h of x. H of x is sine of x over cosine of x. So in reality, h of x is tangent of x. According to our quotient rule, if I have two functions, I'm going to use a very short notation, kind of mental notation, f over g, derivative. I need to do f's derivative in the first half of the numerator, g's derivative in the second half, and subtract those two products, divide by the original denominator squared. So this is kind of an informal, maybe mental notes to yourself. If you get tangled up with some derivative rule, jot them down so you don't forget them while you're taking a mastery test or if you're doing a long homework assignment. Say, all right, here's my quotient rule. So I need to find, let me call this f and this g, meaning f of x is sine of x. So its derivative, as we said earlier, is cosine of x. G of x, the denominator, is cosine of x. So g prime, or the derivative of g, as we decided earlier, is negative sine of x. So if I piece together to get h prime of x, meaning tangent's derivative, since this is an expression equivalent to tangent using trig identities, the numerator is going to look like that. Let's see, f prime times g. Oh, that's cosine of x times cosine of x. Cosine squared of x. So I want to write this way. Cosine of x times cosine of x, you can write it as cosine of x, whole thing in parentheses, squared. The more frequent way you'll see that written, to avoid parentheses, is oddly sticking the squared kind of in the middle of the expression. But cosine squared of x, just as a note, if you want to enter this in GC, you'd have to write it the other way, cosine of x squared. But these two mean the same thing. It's just a notational, avoiding writing parentheses sort of expression that has come to be. So I usually put parentheses around my independent variable input part anyway, so it doesn't really save on parentheses. But f prime of x times g of x is cosine of x times cosine of x. And then we've got minus g prime times f. Oh, g prime times f is negative sine of x times sine of x. So I'm subtracting negative sine of x, otherwise known as adding sine squared of x. Subtracting sine of x times sine of x, or subtracting negative sine of x times sine of x is adding sine of x times sine of x, or adding sine squared. That's our numerator. Denominator is the original denominator squared, so cosine squared of x. And if there's any trig identities that most people remember having taken it, it's that one that you see in the numerator. Cosine squared of something plus sine squared of the same something is equal to 1, regardless of what the something is. Cosine squared of x plus sine squared of x is 1. Cosine squared of 4t plus sine squared of 4t is also 1. Doesn't matter what's in the input spot. That numerator is equal to 1. And 1 over cosine squared, meaning 1 over cosine times 1 over cosine. Since cosine is the reciprocal of secant, this is also commonly written as secant squared of x. Now, do you have to write it as secant squared? No, you could write it as 1 over cosine squared. You can memorize all of your trig derivatives in terms of just sines and cosines, because they can all be written that way. It is a little bit awkward. Sometimes they're faster to remember, and you'll see patterns. If you look through the 6 trig functions and their derivatives, you should be able to see patterns between what the original and the derivative look like. sine and cosine versus tangent and cotangent, secant and cosecant, they all have fairly similar transitions from one's derivative to the other, which makes for nice pairs of functions to look at. But in any case, using quotient rule, we can get this magical secant squared of x that appears in shortcut lists. So on Tuesday next week, we'll talk about some of the steps skipped in that. How on earth did we get that quotient rule defined there? But we'll talk about most of them. Composition of functions, which if I needed to find the derivative of secant of the square root of x or something like that, I'd have to deal with secant's derivatives and square root of x derivatives somehow kind of combined. But it's not quite a product or a quotient, it's something else. So between now and next week, I'm going to have you read the section of chapter 6.3 that's about compositions of functions. It's kind of messy, but there's some diagrams to help through it. You have an assignment that has just a whole bunch of short derivatives to do that is due tomorrow, I believe. Yeah, it's like homework 11 or something. And another one that's due next week that you can probably do part of that by now too. All right, I will see you next week.